So here's perhaps the simplest but sort of non-trivial example of a dynamics problem involving a single rigid body. So we have a single rigid body with no external forces or moments. Okay, so we have a single rigid body with no external forces or moments. So sum of forces external equals 0, sum of moments external equals 0. So this literally is a free body diagram. There are no forces or moments on the rigid body. We are imagining that 0 is some inertial frame and B is a body fixed frame. In other words, a frame that rotates rigidly with the rigid body. And if we do need to use an origin, then the origin of B is at G, but that may not be necessary. Okay. So in general, I just make a remark here that whenever we say acceleration of G or angular acceleration, etc., unless we state otherwise, those linear and angular accelerations as well as velocities are relative to the inertial frame, unless we state otherwise, of course. Okay, so that's the free body diagram. Let's write the equations of motion. Like we discussed a couple of weeks ago, there are two key equations for a rigid body in 3D. One, of course, is the usual linear momentum balance or Newton's equations. Sum of forces equals mass times acceleration of the center of mass. Sum of forces is 0. So mass times acceleration is 0. Mass is a constant, so acceleration is 0. Acceleration is 0 means that velocity is a constant, right? So that makes sense. There are no external forces. Linear momentum is conserved. Velocity is the constant for the rigid body for all time. Okay, so if G has some initial velocity, V sub G of 0, the velocity will remain the same for all time. In other words, if this is the initial velocity, velocity for all time is equal to the initial velocity. Another consequence is that if G moves at all, G moves in a straight line. Because the velocity is a constant, if the velocity is a constant, the only motion that's consistent with that is a straight line motion. So if we have a position vector for the point G, that position vector as a function of time is the initial value of the position vector plus t times Vg at t equal to 0. Okay, so that's the linear motion of the point G. That's all there is to it. Because there are no external forces or moments, all that happens is that G can travel in a straight line if there is a non-zero velocity initially, or if the initial velocity is 0, then of course G just stays put, does not move. Okay, that's all that can happen. So that's linear motion of G. Now what about rotational motion? What about rotational motion? We can ask the question analogous to one above, right? So when the forces were equal to 0, the velocity was constant. Now, is it true that when the external moments are equal to 0, is it true that the angular velocity is a constant, right? You can ask that question. And the answer is no, it turns out. So the angular velocity, it turns out, even in the absence of external moments or external torques, can change constantly. In fact, it does change constantly. So we shall see that in a minute. So the rotational motion of a rigid body is not actually that analogous to the translational motion of a rigid body. Okay, this is the analogous equation though. So the rate of change of angular momentum about point G, d by dt of hg equals sum of moments about G. Okay, so that's the so-called angular momentum balance equation or Euler's equation. It's analogous to F equals ma. Okay, this is the sort of the generalization of sum of moments equals I alpha in 2D, right? So in 2D we had sum of moments equals I alpha. In 3D, because I, the moment of inertia, is a more complicated quantity, namely the moment of inertia tensor, we don't any longer have sum of moments equals I alpha as a correct and complete equation. The more general correct equation is rate of change of angular momentum equals sum of moments, sum of external moments about that point G. Um, Now, because we did not have any external moments, we just set this equal to 0. So d by dt of angular momentum equals 0, which of course means that the angular momentum is a constant. Okay, angular momentum is a constant. Now, angular momentum specifically about the point G is a constant. It so happens that we can prove that angular momentum about any point is a constant. So I'll let you guys prove that. Okay, so angular momentum is a constant, but does this mean that the angular velocity is a constant? Okay, just like velocity is a constant here, is angular velocity constant here? So let's look at this question. So this question, in some sense, and of course all the questions that come after this, is why we created the infrastructure, the mathematical and physical infrastructure for representing these various quantities. So recall B is a body fixed frame, and we want to choose B such that the axes are aligned with the principal axes of the rigid body. Okay, so we have this body fixed frame, and we choose B in a manner that X, B, Y, B, and Z, B are aligned with the principal axes. Okay, what do we mean by the principal axes? Recall that principal axes, if you pick axes aligned with the principal axes, the moment of inertia matrix is diagonal. So that's the last thing that we did. So we have a diagonal moment of inertia matrix in frame B. Okay, so this is the tensorial representation. This is the matrix representation. We'll mostly just use the matrix representation. It's a diagonal matrix, and these are the principal moments of inertia. Okay. So what we're building up to is essentially trying to write an expression for angular momentum using moment of inertia, and then differentiating that, setting equal to 0, and see what we get. Okay, so that's what we're trying to get at. So this is moment of inertia. Angular velocity, let's say, is this quantity, again represented in frame B using EXB, EYB, EZB. Angular momentum is just I omega, right? This is in fact how we defined I, the moment of inertia tensor. Angular momentum is just I omega. If you represent everything in frame B, we can just write them as 3 by 1 matrix equals 3 by 3 matrix times 3 by 1 matrix. Everything needs to be in the same coordinate frame for this to work out, for this matrix version to be worked out, unless we change the definition of things. Okay, so the right hand side is going to be this times this, which gives you this. Okay, so that's this vector. We can write this in terms of vectors, unit vectors. Okay, so that's the angular momentum about point G in terms of the principal moments of inertia about point G, and in terms of the angular velocity of the rigid body. Okay, so what is d by dt of hg? We're taking the derivative of this quantity, and we just use chain rule. I is a constant, these i's are a constant. Omegas can potentially be variable. EX, B, EY, B, EZB are unit vectors. Their magnitude is a constant, but their direction can change if the object has a angular velocity, right? So if the rigid body has some angular velocity, these vectors constantly change. So d by dt of those unit vectors are not equal to 0 necessarily. Okay, so that's what we're going to do. We're going to take this, use chain rule. So we get ixx d omega by dt, iyy d omega yb by dt, izz d omega zb by dt. So that's differentiating the omega part. And then the other part is differentiating the unit vectors, like so. So we need to plug in some values for these unit vectors. So how do we find the derivative of these unit vectors? Um, let's just do one of them, and then the other two are identical. So exb is a unit vector, right, by definition. And by definition, it's fixed in the frame B. It's a constant in the frame B, right? So in the frame B, let's go back to the original picture here. In this frame, by definition, exb is some constant, right? So if you're just sitting in this frame and rotating in this object and you're looking at exb, the direction of exb in this frame is going to be equal, fixed for all time, because it's moving with this frame. It's not moving relative to the frame. But from the viewpoint of this inertial frame 0, exb is changing constantly potentially if the object is rotating. Okay, so so we want to find the derivative of an object of a vector that is fixed in frame B, that is rotating with angular velocity omega. So let me go back to that place. Okay, so exb is a unit vector. It's fixed in B, but possibly changing relative to 0. Recall, so this is something, again, we proved a couple of weeks ago. Recall that for any vector g fixed in B, dg by dt is omega cross B. Okay, so if g is a fixed quantity in a body, and the body itself in a body fixed frame, and the body itself rotating with respect to omega, with respect to some other inertial frame with angular velocity omega, then the rate of change of this vector relative to that 0 frame, the inertial frame, is omega cross g. This is entirely due to the fact that g is now rotating relative to the inertial frame. Okay, so we can now use exb, eyb, ezb instead of g and derive expressions for d by dt of exb, d by dt of eyb, d by dt of ezb. So that's what we do here. D by dt of exb is omega cross exb. This is omega. This is exb. Take the cross product, pretty straightforward, and we get this. Do the same for eyb and ezb. We now have the rate of change of these three unit vectors. Now we can plug in these three equations back into this expression. So we have the rate of change of angular momentum is the part where we differentiate the omegas, and the part where we differentiate the unit vectors, here and here and here. Those were the d by dt of ex, ey, ez. Okay, and of course, because there are no external moments, the rate of change of angular momentum equals 0. The right hand side is 0, and that's it. So now this is some big vector with represented in the frame B in terms of exb, eyb, ezb. We can collect all terms containing esb, all terms collecting eyb, all terms containing ezb, and set each of those coefficients or set expressions to 0. So setting the exb terms to 0, you get this expression. Setting the eyb coefficients to 0, you get this expression, and ezb, you get this equation. These three equations are actually also called Euler's equations. Euler's equations for the motion of a single rigid body. What are these? These are three differential equations, three ordinary differential equations in omega xb, omega yb, and omega zb. Of course, the i's are constants. I's are all constants. There's basically three differential equations. They're coupled differential equations. In the omega angular velocity as represented in the body fixed frame. Okay, we can solve these equations in MATLAB, and that's how we start actually to try to simulate a 3D rigid body spinning potentially in free space in the absence of any external torques, right? So So let me go back here actually. So this condition of no forces and no moments is sort of like satellite in outer space. You can sort of think of it like a satellite in outer space. We'll see that can also exactly the same equations apply if you have a body falling toward Earth but potentially spinning. In any case, these are the three differential equations. Okay, so let's so like we said, we can solve this in MATLAB, um, and we will essentially set up how to solve these equations in MATLAB later in this video, and then also um, actually solve the equations in MATLAB in a subsequent video. But before we actually solve these equations in MATLAB, let's think of some special cases for these equations. Okay, so these are differential equations. It turns out that we can actually solve these differential equations analytically, or at least geometrically, but we're not going to do the complete analytical derivation for its solution for the generic case, but we're going to look at some special cases. So case number one, let's say the initial angular velocity is 0, omega is 0 initially, which means that omega xb is 0, omega yb is 0, omega zb is 0 at time t equal to 0. So in this condition, we can plug these three zero initial conditions in here, and what we get is d omega by dt is 0, d omega xb dt equals 0, d omega yb dt equals 0, d omega zb by dt equals 0. So what that means is that if you start with initial omegas equal to 0, the rates of change of omegas remain 0 for all time. So the object is not moving initially or not spinning initially, well, it will not be spinning forever. It will not be spinning forever, right? So it'll remain not spinning forever. So that's case number one, very simple case. The other two cases, what we're going to do is do that in a separate video.